Alright, so we are looking at the matrix of linear transformation. Because like when we have transformations, we kind of want a formula for it, and so we can use matrices, and it's pretty cool. So if we have the columns of I sub 2 broken down into E1 and E2, we have a linear transformation from R2 to R3, such that our transformation on E1 gives us this vector 5, negative 7, 2, and our transformation on our E2 gives us negative 3, 8, 0. What is a way that we can find a formula for the image of some x in R2, given that this is what happens with our elementary, or our just like our standard vectors. So, well, we know that if we have some vector x, that's going to be with elements x1 and x2, and this is going to be x1 times our vector 1, 0, which is E1, plus x2 times our vector 0, 1, which is E2. Okay. And so, if we have x times our transformation on E1 plus x1 plus x2 times our transformation on E2, then we should be able to get out what we're looking for. So that's going to be x1 times 5, negative 7, 2 plus x2 times negative 3, 8, 0. And so now we have a linear combination, and we can add these up. And so we get 5x1 minus 3x2, negative 7x1 plus 8x2, and 2x1s, and 0x2s. So how can we write that as a like a formula? Well, we just take out our x1s and x2s and make this into a matrix. So that gives us a matrix of 5, negative 7, 2, negative 3, 8, 0. And that we can pull from actually these columns here. If we just put those together, then we do have our matrix. So we have this. We're taking Rn to Rm with a transformation, a linear transformation T. Then there's going to be a matrix, a unique matrix representation that can show us what our linear transformation T is for all x's in Rn. And just like we did before, we can just take our transformation on our columns of our identity matrix, and we will be able to construct our A. And this is called the standard matrix for the linear transformation T. Just a quick sketch of why that is. Well, remember, we can find our vector x, and in terms of just our identity matrix multiplied by x, and so that's our E1 times E1 to En as our columns, as our column vectors, and that's times our vector x, and because our identity, like just multiplying by the identity, doesn't do anything. And so if we're taking our transformation on this x, our linear transformation is going to be the same as our linear transformation on our weighted E columns. So we have that times x1, and adding up that with our xn, with our en, and then we can write this as our transformation on E1 to our transformation on En, all multiplied by our x1 to xn's. which is just the other look at matrix multiplication, where we have weighted, like we have a linear combination, and also write it as multiplication. And that, so this is A, and this is X. So we get AX right there. So if we want to find the standard matrix A for our dilation transformation, where we're taking our matrix, or taking our vector and we're dilating it by a factor of 3, we just want to take everything and multiply it by 3. And so how do we do that? Well, we take our elementary, or our standard vectors, and we multiply them by 3, like scale them up, and then put them together into a matrix, and we get 3, 0, 0, 3. So there's our standard matrix for our dilation, where we're taking essentially our identity matrix, scaling up by 3. So let's say we have a transformation that's going R2 to R2, and we're rotating our points through the angle phi, or counterclockwise. And so that's nice because we can utilize trig. So looking at this, this is what's going to happen. We have some point 1, 0 or 0.01, and in order to rotate it, we need to map to our cosine of phi, sine of phi location. So that's cosine and sine here in our first column. And then from up here, we need to have negative sine of phi, cosine of phi, right there. So we're going to skate through this pretty quickly. We're going to go over this in class too, so be mentally prepared for that. So when we have reflection through the x1 axis or the x2 axis, we just need to negate, right, whichever column we need to negate properly, so that what we end up with is a reflection across the axis. If we're reflecting through lines that are not the axes, then we need to swap the rows so that we reverse what our coordinates are. And if we're going through a different line, which way is this? If we're going through a line this way, then not only do we need to swap the locations, like the x1 and x2, but we also need to negate them in order to get into the opposite side. Reflecting through the origin to do this standard matrix. If we're looking at contractions or expansions in the vertical and horizontal directions, these are going to be a scalar, some scale factor that's happening. And if we're only doing it in one direction, then that's the only part that we interact with. And when we have our k is between 0 and 1, then we're going to get a compression horizontally or compression vertically. When we have a k that's greater than 1, then we're going to have a expansion or a stretch. We talked about shear, so shearing sheep, remember, it's my favorite. But shear in the horizontal direction, that means that we're taking we're taking a 0 and replacing it with a scalar. And doing horizontal shear means that we're taking we're putting our k in our row 1 column 2 position. But if we have our k in our row 2 column 1 position, then we're having a vertical shear. And projections. So when we have projections, that means that we're effectively taking away some information. So we're zeroing out that coordinate or that variable, that component is getting zeroed out. And so that can be onto the x1 axis, onto the x2 axis. If we're working in higher dimensions, then accordingly zero out things. So get ready for a super not fun game in class. This is one of my favorite Pokemons, so that's fun. Alright, so we have onto and one-to-one, and looking at these, we have a mapping T is going to be onto if each B in Rm, so in the codomain, is the image of at least one X in Rn, or in our range. So as long as we have our range, if each B in our range is the image of at least one input X vector in our Rn space. And a mapping is one-to-one if each B in Rm, so in our what we're mapping to, is the image of at most one X in Rn, so there's no repeating Rn's that are mapping to the same thing in Rm. Okay, so for our linear transformation with this standard matrix, does T map R4 onto R3, and is T one-to-one? So this is conveniently in echelon form, so that's nice. And so we can see that we do have a pivot in each row. So because of that, we know that we have onto, that T is onto. But we do have a free variable in X3, so T is not one-to-one. So yes onto, no one-to-one, not one-to-one, because we have a free variable. So if we have T is a linear transformation from Rn to Rm, T is one-to-one if and only if, so that's if and only if we're going this way. The equation T of x equals 0 has only the trivial solution. So we have one-to-one if and only if we have only the trivial solution. And just a quick justification for that. So since we have linear transformation, then T of the 0 vector has got to be 0. And if it's one-to-one, then T of x giving us 0 is only happening one trivial time when x is the 0 vector. Otherwise, there's going to be b in the image of at least two of our vectors, u, column u and v, in Rn, with u not equal to v, with T of u equaling b, and T of v equaling b. So then if you take the difference of those, oops, it's v, then you're getting T of u minus T of v, right? Because it's a linear transformation, so we can do that. And so we're getting our b vector minus our b vector, and that's 0. But this being 0, and remember that u is not equal to v, so then this is not 0. And so there's more than one solution, and so either we have only the trivial solution, and so we have one-to-one, or we don't. That if we have not a trivial solution, like that, then we don't have one-to-one. So if we have T, and that gives us a linear transformation from Rn to Rm, and A is our standard matrix for T, then we have a couple things. We have that T maps Rn onto Rm if and only if the columns of A span Rm. And that's because if we have columns that span Rm, that's happening if and only if for each b vector such that Ax equals b, that's consistent. Meaning that there is a solution, right? Consistent systems have a solution, at least one solution. And that's if and only if we have our transformation that takes Rn to Rm. And we have T is 1 to 1 if and only if the columns of A are linearly independent. So, meaning, well, like linearly independent mean, or, yes, so we have T of 0, so this is A. T of 0 is going to give us, or T of X is going to give us, T of X gives us 0, and A times X equals 0. Those are the same except for like notation, right? So if, thinking back to what we had before, up here, that T of X equals 0 has only the trivial solution, is if and only if with our T is 1 to 1. So, we have, 1 to 1 if and only if AX equals 0, right? And that being the only time that that happens is a trivial solution, and that's only happening, it's only trivial. That's only happening if A's columns are linearly independent. Because if we have linearly dependent columns, then we can have the non-trivial solution to give us AX equals 0. But if we only have the trivial solution, then our columns are linearly independent for A. So last thing, if we have this transformation, show that it's 1 to 1. So we know that it's 1 to 1, I guess. And then we're also asked, does this map R2 onto R3? So let's try to get our standard matrix. And we can do this just by looking at it. So we get 3 and a 1. 3 and 1. 5, 7, and 1, 3. So looking at that, we have 1 to 1 because our columns are linearly independent, right? Columns are, what's our columns? Our columns are linearly independent because they're going in different directions. So, yes, it's 1 to 1. Does the T map R2 onto R3? So the question really is A's columns, do those span R3? Do the columns of A span R3? And the answer is no, because we only have 2 vectors. We only have 2 columns, and so that can't span R3. Because it's just going in 2 directions, you're going to end up with a plane like this. And so, no, this is not onto. So T does not map R2 onto R3. So that about does it.